Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be finishing up chapter 2, looking at enthalpies of a system. So last time we brought up we can get the enthalpies of reaction by taking standard state enthalpies, often of formation, looking at the product enthalpies, subtracting out the reactants, and getting our reaction. The problem is these assume we're at standard temperature and pressure, but a lot of the times we aren't. So what we're going to do today is really figure out how we can do our temperature corrections. Is worth noting, if you need to and you're looking at a non-ideal system, for an ideal system, we don't really need to correct for the pressure. But if you do need to correct for the pressure for a non-ideal system, you can use a lot of these same principles and instead really focus on using the internal pressure and the um, isothermal compressibility. But we're going to focus on this temperature term. And the way we can really do this is we can just say we're still doing products minus reactants, but I'm going to correct for the temperature of the product and the temperature of the reactant. So let's say I'm trying to determine the enthalpy of reaction at some new non-standard temperature. Well, I can do this by saying, hey, what's the enthalpy at this new temperature for the products, and what's the enthalpy of the reactants at this new temperature? Well, if I know the standard state enthalpy, I can say, well, I know how to correct for the enthalpy uh, of a species with temperature. It's just the heat capacity times that difference in temperature. And I can do this for the products, and I can do this for the reactants. Now what we can do is, hey, notice uh, we have our enthalpy terms and we've got our heat capacity terms. So we're going to go ahead and do a quick mix and match. And we can say, hey, wait a minute. That just means I'm looking at the difference in enthalpies of the reactants products at the original temperature, and I'm looking at the difference of the heat capacities times the change in temperature, for again, the products minus the reactants. Well, you'll notice this first term is just going to be the enthalpy of reaction at T1. And notice we have a common delta T term on the heat capacities. So that means what I'm really left with is the difference in between the heat capacities for the products and the heat capacities for the reactants. This is known as delta Cp. Now, it is worth noting, if we do have stoichiometry at play here, the differences in the differences in the heat capacities will be calculated using the same stoichiometric techniques we use for the differences in the enthalpy. So again, we're just doing the same thing, but now for the heat capacities. Now, this idea that we can figure out the enthalpy reaction at a new temperature just by adding in this delta Cp, delta T term, is known as Kirchhoff's law. And it actually works fairly well, but it is worth noting it only works in temperature regions within about 100 Kelvin of the original temperature. And the reason here is actually relatively straightforward. We're assuming these heat capacities have no temperature dependence. And as we said, that really only holds for small temperature regions. So if I'm looking at trying to apply this for larger temperature regions, well, my apologies, you're gonna have to use the expanded heat capacities and do the hard integration. But most of the time, we're interested in conditions that are relatively near standard. So that means we can use Kirchhoff's. Now let's go ahead and put this into application for a real idea. So let's say I'm trying to figure out what's the enthalpy of fusion for ice at 0 degrees C, because it turns out that's when ice melts. The problem I have is if I go ahead and try and figure this out, I'm going to have to look up the enthalpies of formation for ice and water. But notice these pesky knots. That means my enthalpies of formation are for 25 degrees, not 0, because they're for standard state. Which means if I tried to calculate it with these standard state enthalpies, I'd have a wrong answer. So one of the good ways to try and guide our way through one of these is to build up a thermodynamic cycle. And this shows the idea of the enthalpy going from from ice at 0 degrees to water at 0 degrees would be the same thing as this very unrealistic model of taking ice, keeping it as ice at 25 degrees, then melting it, and then freezing it again, or then cooling it down again. So I'm never going to have ice at 25 degrees C, But this is the beauty of Hess's law. It doesn't matter if I take an unrealistic pathway, as long as I have the right beginning and ending step. So these two pathways will give me the same result. And this is why we love state functions and hate path functions. So we can calculate each of these steps individually. So the part we want is this enthalpy of reaction at 0 degrees. How I get there is by adding together three terms. First, how much energy does it take to heat up ice from 0 to 25? How much does it take to melt ice at 25? And how much does it take to cool down the water? So we can add together these three terms each way. And by adding together these three terms, you'll notice that the difference in between the heat capacities of the liquid and the solid can also be written as delta Cp. So hey, look, we showed that working through the thermodynamic cycle gives me the same result as Kirchhoff's law. So now let's actually go ahead and plug in some numbers. So we can figure out the enthalpy of reaction by simply taking the enthalpy of my product, water, again, that negative 285, minus the enthalpy of ice, which is negative 291. So thus we get the plus. And then we're going to take the difference in between the heat capacities of my product, water, and reactant, ice. So again, we get that. And notice the temperature difference here is negative 25. Because my standard is 25, we want 0. So that delta T here is negative 25. And if we put this all together, we're going to have a couple of key things here. So notice, by taking this first difference, we find the enthalpy of fusion at room temperature is 6 degrees. But once we subtract out that heat capacity term, we find out that uh, um, the enthalpy at 0 is actually about 1 kilojoule per mole lower. So if we tried to use the standard state conditions, we'd actually be off by, about 12, about 15%. So significantly wrong. So again, especially if you're looking at larger temperature regimes, or you want to be more precise, you really want to go ahead and correct for these differences in heat capacities. But it is worth noting that sometimes Kirchhoff's law isn't good enough, and we might actually want to have our initial and final states be different. So what would happen if I'm trying to turn negative 20 degree ice to 20 degree water? This is actually a much more realistic case. So we're taking ice out of a very cold lake, and I want to bring it up to more or less room temperature, so about 73 degrees Fahrenheit. Now notice at this point, I can't use the simple Kirchhoff's law because our initial and final state aren't the same, but I can still use my thermodynamic cycles. So this will still be the same as going from ice at the cold temp, heating it up, then melting, then cooling it back down. The bigger thing is we're now heating it up more and cooling it down less. So we can still get this by taking the heat capacity of my ice times the change in temperature times that enthalpy of reaction. So that's still standard state reaction we have, which is about 6 kilojoules. And now my new heat capacity of liquid water and how much I have to cool it. So now we've broken it down into these three components. And so even though this pathway is unrealistic, the difference from the starting and ending still works. And in this case, we find out that it's now about 7.3 kilojoules. So about 1 kilojoule higher than expected from standard conditions, because it turns out we had to heat it up a lot more. So we had to heat up that ice a lot more, and we didn't get as much of a gain from cooling it down. So this is going to be very useful whenever you're trying to turn standard reference temperatures into the ones you actually care about. And in practice, is one of the more useful skills we use this semester. So that brings us to the end of looking at the enthalpies and energies of reaction. Next time, we're going to finally start looking at not what happens if a reaction happens, but trying to figure out if a reaction happens. So next time, we move on to entropy. Until then, take care.